Welcome to Lecture 12, Free Body Diagrams and 3D Rigid Body Equilibrium. In this lecture, we'll be discussing the equations of equilibrium for rigid bodies in 3D, as well as 3D free body diagrams. In the last lecture, we established that the equilibrium of a body is expressed by these two equations. The first being that the sum of all of the forces acting on the body is equal to 0, meaning that the body is not translating, it's not moving in space, and that the sum of all of the moments on the body is equal to 0, meaning that the body is not rotating. Here are those equations shown in Cartesian vector form, and remember that in order for these equations to be true, each of the components in each of the equations must be equal to 0. In scalar form, we show that as the sum of the forces in each of the x, y, and z directions are equal to 0, and the sum of the moments about each of the x, y, and z axes are equal to 0. So we now have 6 equations to use in our 3D rigid body equilibrium problems, which will allow us to solve for up to 6 unknowns. Similar to the 2D case, prior to applying the equations of equilibrium to a 3D rigid body equilibrium problem, you will need to create a complete and accurate free body diagram of the rigid body. Let's look at some support reactions in 3D. You can find a more extensive table of support reactions in your text, or should be able to easily Google one. Now, as a general rule, if a support prevents translation of the body, then a force is developed on the body in the opposite direction, and you would need to show that force in your free body diagram. For rotation, if rotation is prevented, a couple moment is exerted on the body by that support. No different than the 2D case, but realize now that instead of 3 equations of equilibrium like we had in the 2D case, 2 force equations and 1 moment equation, we now have 3 force equations, x, y, and z, and 3 moment equations about the x, y, and z axes. So a support can restrict or prevent translation and rotation in a total of 6 directions. Let's look at one of the simpler support reactions, a smooth surface support, where you can see that a smooth surface is not going to, there's no friction, is not going to restrict translation in the plane of the surface. It's not providing any restriction to the body rotating about any of the 3 reference axes. The only thing it's doing is providing a normal force, a force perpendicular to the surface on the body. So out of the 6 potential reactions, the 3 force reactions, the 3 moment reactions, only 1 of the force reactions is present. Another common type of support is called a ball and socket, otherwise known as a ball joint. Here you can see that it's restricting movement restricting translation in the X, Y, and Z directions. So not being consistent with Xing these out, but hopefully you're following along. So I'm going to show the three force components in the X, Y, and Z direction in the free body diagram. And it is not preventing rotation about any of the three axes. In other words, this ball joint, the body here can rotate about any of the three axes without restriction. So I'm not going to show the moment any of the three moment reactions on the rigid body. Another common support is a single journal bearing, and by definition the journal bearing does not restrict movement of the shaft shown here along the axis of the shaft. So we're not going to show that force reaction. It also doesn't restrict the rotation of the shaft about the axis of the shaft. I mean, that's usually the point of it, that this might be a shaft that's spinning in that bearing. So we're not going to show those two reactions, but it does restrict or does provide a restrictive couple moment in both the axes perpendicular to the shaft, shown here, and you can see that it also keeps the shaft from moving in this direction, sideways or up and down. Okay, so here we've got 4 of the 6 reactions with a single journal bearing. Let's look at a hinge. A hinge is going to be even more restrictive than the single journal bearing. A hinge is going to keep the rigid body that's attached to it from moving in the X, Y, and Z direction. Didn't show it very well here, but put that other one there. And so we show those 3 reactions. And the only rotation motion it allows is, the opening and closing of the hinge. Okay, so we're not going to show that moment, but it restricts rotation along the other 2 axes. So a hinge is, when we have a hinge, we're going to show 5 out of the 6 support reactions. An important note regarding 3D free body diagrams involves the journal bearing support and the hinge support that we discussed on the previous slide, as well as a pin support, which we didn't discuss previously, but is very similar to a hinge. And each of these supports allows rotation of the rigid body about a single axis. Well, for purposes of this example, let's assume it's the x-axis, and they prevent rotation about the other 2 axes, namely the y and the z axis. So if we were showing the reactions for any of these 3 supports, we would include 2 moment components in that set of reactions. Now this is when we have a single use of a journal bearing, a hinge, or a pin. When we use these supports in conjunction with other properly aligned bearings, hinges, or pins, in other words, if we have a body supported by 2 or more journal bearings, or 2 or more hinges, or 2 or more pins, or some combination of those, in other words, a single bearing, a single hinge, or 2 bearings and a hinge, or the combinations are infinite. In these cases, the forces provided at the supports are adequate to support the rigid body and provide equilibrium. And in those cases, we're not going to show the couple moments on the free body diagram. So this is probably at first not going to be intuitive, but this is a common practice for drawing free body diagrams involving these types of supports, and it's going to lower the number of unknowns such that we can solve 3D rigid body equilibrium problems using the 6 equations we have. So let's look at some examples here. In this first example, we have a bar, a bent bar, supported, loaded as shown with a 500 Newton force and a couple moment, and it's supported by 3 journal bearings at A, B, and C. And if you think about this, imagine that this bar was only supported at A by a single journal bearing, and there's no bearing at B or C. Now in that case, it's probably not hard to see that, okay, there are going to be moments there. A is going to be, that bearing is going to be providing restrictive moments in about two of the three reference axes. But by having B and C also helping to constrain the bar, if you think about it, you can see that now those moments aren't present at A anymore. And any moments that would be present at B if we didn't have bearings at A or C are not there, and the same for the bearing at C. If we didn't have the bearings at A or B, there would definitely be moments about provided by the bearing at C. But since we have the combination of the 3 bearings on there, as we said, the forces, the reactive forces at each bearing are keeping the bar in equilibrium, and we are not going to show the moments. Now notice here we have 6 unknowns: A sub Z, A sub Y, the 2 components at B, the 2 components at C, and we can write 6 equations, equilibrium equations for this situation. So we should be able to solve for all of the forces, unknown forces acting on the bar. Let's look at the second example here. So here's a pin connection, what's considered a single pin connection, and it basically, you can just consider it as a hinge, at least in this problem, in this example. And notice that we don't have any additional pinned supports or hinges or journal bearings. So when we draw the free body diagram for this example, at the pin, when we remove the supports, we're going to show the 3 force components as well as 2 of the restrictive moment components. The only rotation that's not restricted is rotation about the y-axis, m sub a sub y, and you should be able to see that that's just like a hinge. It is free to rotate about the y-axis. Now in this example, it's probably a little easier to envision that, yeah, there are definitely couple moments present at that support because we have this tension pulling on that bar, trying to rotate it about the support. But similar to the first example, how many unknowns do we have? We have 5 at the pinned support, but then only 1 additional unknown, and actually we would need to know the direction of T in order to keep it to 6 unknowns and be able to solve with our 6 equations. Okay, let's look at the last example here. So we have this plate that's being supported by a hinge, a journal bearing, and then a ball bearing or a roller at B. And first, let's imagine that the roller is not there, that ball bearing is not there at B. Now, if that's the case, even though we do have a hinge along with a journal bearing, you can, I think it's intuitive that, should be intuitive that when we press on that plate with a 400-pound force, assuming B is not there, okay, that we're going to have moment reactions at both A and C. Okay, so it's not a hard, fast rule that just because you have multiple supports that you can ignore the moments at those supports. But that roller bearing is there, and so now it's hard to put it back, but there's a force there being provided by the roller bearing at B. And now, given that situation, hopefully you can see that there are no moments being created by the reaction, by the supports at C and A. So it's a case-by-case thing when you can ignore the moments and when you can't. Most of the problems you'll see are pretty straightforward. It should be obvious that the situation is such where you can ignore the moments. So the free body diagram in this case for the hinge has the 3 components of force X, Y, and Z. The journal bearing has 2 components of force, and the roller, the ball bearing, just provides a force normal to the surface of the plate. And here again we have 6 unknowns. We can write 6 equations and we should be able to solve for those unknowns.